right, welcome everyone to this very special black hole mapper demographics telecon, where Hengxiao and Qiaoya have gracefully volunteered to give us a presentation about PyQSOFit, first from sort of a design of the software and then from a user perspective. And I'm sure this will benefit a lot of us because it's impacting one way or another the science we do with the spectra. So thanks a lot for your contributions, and please take it away.
Okay, and thanks for your invitation, and also thanks for having me here. I'm Hengxiao Guo from Shanghai Astronomical Observatory, and today I'm going to talk about the code PyQSOFit. First of all, I need to apologize. I haven't write a doc for this code before, so a lot of users may be still not very clear about how to use this code correctly, and here I'm going to talk about the Python version of this code, and Yue also have a ideal version for this code. And currently we have two kind of versions of this code. One is version 1.1, and another is 1.2. And Colin Burke here made a lot of contribution to the new version. And okay. This is the outline of my talk, and first I will give a brief introduction of this code, and then I will talk about the structure of this code and following different components in this spectral fitting, and then I will give you some examples of this spectral fitting code, and finally I will briefly talk about the future prospects. And after my talk, Qiaoya will talk about his experience on application to this code to some DR16 quasar catalog. And as we know, for agent we have a lot of components in the for the agent, and in the UV and optical UV and optical reference, we have different components, emission lines and continuous from different components. It looks like this, and here is also a typical spectra for a quasar, and you will see there's a lot of information in this spectra, and you can measure the black hole mass using line width and also the continuous luminosity, and also you can know the environment of the property of the surrounding environment around the black hole, and also you can use this spectra to get some information about the kinetics and the dynamics of different components around the black hole. So this is very important to get this information from the spectra. So we need a tool to get this information correctly. So we write a Python version of the PyQSOFit to get the information of this from the spectra. And the primary goal of this code is to measure the black hole mass using different emission lines. And before we have an ideal version, and we want to transfer this to a Python code because at that time most of the people are already using the Python to do the research, and already ideal is very old for some old people. And also for this code, we have a lot of different versions for this PyQSOFit, for this QSOFit. So every time when we want to use do some science for specific science, we need to choose a right version. So we have a lot of versions for this code. So we want to combine all these versions into one published code. So we were trying to write a new code and publish it. And finally, it's very interesting. our group is criticized by QSOFit group. So as I mentioned, we all the code are private, so there's no released and published public codes for spectral fitting. So we trying to publish our own code. So, and as you know, so here is a history of our code, and as you know, there's a lot of group in the around the world. They all have a agent. They are working on agent, and almost every group has their own code to do the spectral fitting, since it is not very difficult, and there's no secret in the code, so it's easy to write. And our code is come from originally, I believe it's come from Ting Gui Wang's group from USTC around 2005, and US group learned a lot from like the structure code structure from their group. And I also learned a lot from indirectly from their group. And after I moved to US group, and at that time, Shu Wang is also there. He is another expert for spectral fitting. So we together write this code, and it takes around 1 month to write this PyQSOFit code, and also take another month to do the test for this code. So this so version 1.1 is a stable version. And after that, recently, Colin Burke also updated this code to version 1.2, and the key difference is we just change our kernel and from KMP fit to LM fit, and both of them are based on the least square method. And another major change is before we only have we are only able to tie two groups of narrow lines, and for the new version there's no limit anymore. And also for the new version, we have added this MCMC method to calculate the statistical error. So, in current market, there's another there are two other codes to do this quasar spectral fitting, and one is QSFit, and another is Badass. And as you know, the QSFit code is written in ideal language, so it's not easy to use for some young people. And also, they just only when they fit the host, they just only use one host template, very old, with 5 gig years, I remember. And so it's difficult to do the host decomposition for all of the quasars. And also, according to other groups' results, their successful rate is not high as our code. So maybe their code still needs some updates. And for the Badass, they are using a Bayesian method to do the fitting. And so it will be very slow, and sometimes use fitting one example, fitting one object will take up like half hour or so. And the second is they fit all the components together. It means if your fitting is failed and you want to debug and figure out where's the problem, it's not easy because all the components are fixed blended together to do the fitting. And finally, is the successful rate. I only have a student to do the test, and it seems their successful rate is we are still not very clear about their successful rate, and maybe we are just not familiar with their code, and maybe we just their code is still have some problem to do all the strange spectrals. And here next, I will talk about the main structure of our code. And what you need to do is just set up the line parameters and also the fitting keywords for this code. And here I want to emphasize So for the following slides, what I'm talking is based on the version 1.2, the new version. And after you set up the parameters and the keywords, and the code will do the rest of things, like prepare for the spatial fitting, and do the host decomposition, and fit agent continue, and also fit the emission lines. And finally, you can, if you need the error bars for different parameters, you can run the Monte Carlo method or MCMC method. We have two kind of methods available for the new version. And finally, it will plot a figure for the final results. And if you don't like the style of our figure, you can plot your own figure. And here is emission line parameters, and you can see we have a different complex. This means when we after we finish the fitting for the continue, we will try to fit the emission line, like for the H beta region or H alpha region, and here we separate the emission line fitting for two different groups, and for the complex one, you can see we just fit all the things in around the H alpha, and here is a line center in the vacuum reference, and next is the line name, and here is the boundary of the complex, the minimum reference and the maximum reference, and so just here is a line names in different in this complex. And for the broader components, you can choose like 0 to 3 Gaussians for the broader components. And for narrow components, you usually set to 1. And if you want to add another narrow component, you can just add another row for around here. And don't try to change the number here. And for the next is the line scale, and here line scale. If you set the line scale to be positive, it means you are fitting the emission lines. And if you change it to negative values, it means you can use it to fit the absorption lines. And next is line weight, and here's an initial value in log space, and here's a mean line, the boundary of the line weight. And after that is velocity offset, and you can change. This column is not very This column is not very important, because if you do not have a very large velocity, you don't need to change this column, and just make sure they keep them the default values. And next is velocity index, and here means you tie if you want. Here 0 means we set it free, and if you want to tie different velocity of emission lines, you can set it to 1. If also like here in the same complex, if you have a different in narrow lines, if you want to tie the velocity together, you can set the different lines into the same number. Here means here also different lines are set to 1, means all of them are also velocity are tied together. So it means the line center are tied together to the theoretical one. And next is the line width. It is the same as the velocity, and if you set it to 1, means all the line widths of the narrow components are tied together. And here next is flux index. Here means if you want to tie two specific lines, like nitrogen 3, you can set them to you can set the ratio to be 1 to 3, and here for one group is here means 1 means for the first group, and 2 means for the second group. You can also tie the solver line. And this last column is the file parameters. If you set it to be 1, means it is free, and if you set it to 0, means it is fixed. And this function, this column is used for the multi-epoch fitting. And if you want to fix some narrow components between different epochs, you can set it to 0. And next is I've got for this code we define the narrow component is around below 1,200 kilometers per second, and here this number 0.0017. Here it means it's around it's in the log space. So if you translate it and transfer it to in the linear space, it's around 1,201. So it means if you have a narrow component that hits the boundary, so it will be slightly larger than 1,200 kilometers per second. So if you want to make them slightly lower than this value, you just need to change this value. And I want to emphasize that
Sorry, I was typing it in, but it's faster if I ask it this way. About the min wavelength and the max wavelength, this is indicating the range where you are looking for the continuum, or it is the range in which you are searching for the line, because you have the redshift. So in principle, the lines cannot be much farther than the expected. So searching within 400 angstrom will be a lot.
What do you mean? You mean here? Here is just for the here is just for the line complex, not for the continuum. Here just for emission line fitting. Not here is not related to the continuum fitting. And later I will talk about the how to define the region for the continuum fitting.
No, so but my question is, let's make it differently. So what happens if, sorry, if you can go back to that table? What happens if instead of writing 6,400, 6,800, I write 6,560 and 6,570? Because we know that the redshift, so the object, especially for the broad line, should have the peak more or less around 6563, 6564.
Yeah, you mean you want to get a narrow region for the line complex? Yeah, it could be. You can do that. You can do that.
Okay.
If you just if you can get a nice fitting, it's no problem for the boundary of this.
Okay.
Of this, yeah.
Thanks.
And there's one more question.
Yeah.
Hi, Hengxiao. I'm just wondering, so for fitting the absorption line, if with the minimum scale to be negative, that means that actually it can fit like positive or also negative lines, which means emission lines or absorption lines, depending on how the line looks like.
You mean you want to fit both emission line and absorption lines?
So I mean there's like a minimum scale, but there's no a maximum scale. So looks like that it's
you can
free.
If
looks
you
like
want
it's
to
free.
if you want if you want to
go ahead.
fit an absorption line, you can set it initial values could be a -1, and set the minimum value to be also -1, like -1.10 to 10 or and set the maximum to 0, then you will get a negative value for the negative flux for the absorption line, and you can. Yeah, it's not difficult.
Yeah, so it's like manual settings, not like automatic setting, right?
Yeah, this is a disadvantage of this code, since our code is designed to fit the emission lines, not for the absorption lines. So if you want to fit an absorption line, you need to manually control the different parameters.
I see. Thank you.
Yeah, no problem. And next is the fitting keywords for this code. And here is the input is very easy, and you can see the lambda is observed reference and the flags and error bar errors of the flags and weight shift, and I and deck is for the reasoning. And this is optional parameters from Sloan and plate ID and the major and the fiber ID. And if you want to, here is fitting keywords, and like here, this is a smooth equal to 1 means there's no smooth for the spectrum, and you can set to 2 or 3 means use a cut box for 2 pixel smooth or 3 pixel smooth. And here next keyword is and all mask, and this means if this comes from the Sloan output, if you input the and all mask into the around here, you can set it to true, and later I will give an example how to use it. And next is reading, and if you input the I and deck, you can turn on this parameter, and it will do the dividing automatically. And the next one is reject the bad pixel, and usually I will turn it off, since I have some concerns about this function, and later I will talk about it. And here's a wave range, and you if you want to do a local fit for the spectrum, like just for the H beta region or H alpha region, you can set a boundary for your fitting range. And the next one is reference mask. If you have like strong absorption lines around your emission lines, you can set a mask region and just block this region and in the fitting. And the most important 3 steps is are the host decomposition and the continuous fitting, and also the error estimation. And for the host composition, you need to turn on this parameter. This means set it true to do the host decomposition. And here, if you set the BC03 to false, means you are using the PCA method to do the host decomposition. And if you set the BC03 to true, it means we are using the SSP template to do the host decomposition. And the next is continue fitting, and usually we will turn on the iron template. We have two kinds of iron template. One is a UV template, and another is the optical iron template. And for the polynomial component, this is sometimes account for the reasoning for the local AGN. And the next one is the BAMO continue. Sometimes usually we will turn it off, since we don't need it usually. And for the reject absorption lines, this only turns on when the when your continue there's a lot of absorption lines in your continue, and you can't find the correct continue. So you can turn it on. And next, in the new version, we offer 2 kind of two kinds of method to do the error analysis. One is the Monte Carlo method, and another is the MC method. And you can, if you turn on the MC, usually we set the unsampling means unsampling here means iteration numbers for the MC method. Usually we set it to 50, and for the MC method here means the unsampling means the chain length of the chain. So so we will talk about this slide. Give you some basic ideas of the preparation. And the first is the end-all mask. You can see the real one is after we remove some bad pixels labeled by the and more all mask. And this is you can see some telecon lines are masked. And second panel is we reject some bad pixels here. This function here we just reject 10 most possible bad pixels in the spectrum. So there's a problem here. When your spectrum is very high signal about very high signal noise ratio, this function will consider some like very highest flags pixel or pixel in the oxygen 3, like around here. He will consider this is also an outlier, so it will reject some top pixels in your narrow line, So usually we will turn it off. If you want to turn it on, you need to check. I suggest you to check before and after the correction to compare whether some useful data was rejected. And second panel is third panel is reading. We are just using the dust map from Hengxiao and extinction law from Fitzpatrick and do the reading correction. And the next step is host decomposition. We have two different kinds of methods. One is the PCA method, and another is the simple stellar population templates. And here I have an example using two different methods, and you can see the results are pretty similar. And for the PCA method, here we are using five templates from the galaxy and 10 templates for the quasar. According to we are using the templates from Yelp, a paper written by Yelp, and according to his suggestion, 5 templates for galaxy and 10 templates for the quasar is already enough for fitting more than 98% quasars. So this I said this is a default setting. So it almost can fit all kinds of different quasar spectra. And for this parameter host line mask here is like this. When you're doing the spectral decomposition, you will have some absorption line or emission lines in the host templates. And what we care is the agent spectra, and how we calculate the agent spectra is using the original data and minus host template. And if you minus the emission line here, sometimes you will get some very strange features around here, like spikes or very deep gaps in the broad emission components. And so it will be very difficult to do the fitting for the later AGN spectra. So sometimes, usually I will tend to choose to do the fitting means we count all the emission lines in this spectra come from the AGN, not come from host. And for the BCO3 method, and here we just we can turn we can turn both of these two keywords to true, means we are using the PyQSOFit method, and here for the agent for the Quasar PCA template, we are still using the 10 templates, and for the Galaxy template here, you can change the numbers to determine how many PyQSOFit templates you want to use. And sorry for the confuse of this name, and this is still the PCA Galaxy, but it also determines how many templates we should use for the PyQSOFit model. And for the host Galaxy fitting, and most frequently asked questions, some user will got this error and this warning, I should say. They got negative host flags larger than 100 pixels. Here means when you do the host decomposition, like around here, you will get sometimes if the original data is very strange and your template is very hard to do the fitting for this code for your data, and you will get some negative flags for the host component. And here, then if you so we will sometimes we will consider this situation as a failed decomposition. So this is because we have a lot of agent templates, and we also have a lot of host templates, and we just doing the linear combination for these templates, and we have a coefficient for every template, and if the coefficient is negative, then you will get a lot of negative values for the host template. So we will consider this situation as a failed. And in the new version, we have changed our strategy, and we have we have forced coefficient to be positive. So you will navigate this warning again. And but in trade-off, sometimes the successful rate for host decomposition will be slightly lower.
Sorry.
And yeah.
Can you go back to the slide? So I am following, but I have just a comment on the fact that the PyQSOFit does not have emission lines from the host. This is just a continuum. So we have to be clear that for the lines that can be generated by the host and by the AGN, the narrow component still have a contribution from the host, because the PyQSOFit does not have the emission line, correct?
Yeah.
Okay.
You can, if you want to account the emission lines in the host, you can set it to false. But maybe you will meet us small problems. Sometimes when you're fitting the agent component, it will be more challenging, since you add some flags into the agent flags agent spectra. You will maybe see as a shift or something here. So it will be maybe have sometimes fitting is not so perfect as set it to true.
Okay, thank you.
There's another question by Katarina.
Yeah. Mm-hmm.
Katarina, can you ask your question?
Yes, I can ask my question, but I apologize if maybe there's some background noise. I wanted to know, how do you compare these two methods, just the PCA or using PC03? If you have to use the uncertainties, or like, how do you know which one is the best?
Yeah, next slide I will talk about our comparison. Here, for host decomposition, it is the most difficult part in this in Quasars, like for some with some very low signal to noise ratio spectra, and one student, one colleague from USTC was working on this project, and our goal of this project is trying to do the decomposition for all the stone spectrums at a low lift shift. And our idea is use stone spectra, and for the agent, we're still using the PCA templates, and for the host, we are trying different models, like for the PCA method, and also for the SSP template, also sometimes for the Stellar templates. And then we got the host data using the original data minus the agent model, and we can get the host component, and then you can use the PPXF to get the host properties. And what we care here is just the velocity dispersion, and because we are care about the M sigma relation. And the successful rate for the host decomposition with PCA is around 16 on average. And the key problem here is a lot of low signal noise ratio spectra. And here is some comparison results. Here the idea is like this: we are using we just pick out some early type galaxy spectra, and they are showing strong absorption lines here. And we are here is a composite of a lot of hosts, and we are using PCA method, and also using SSP templates, and also Stellar templates to do the fitting for the host for the pure host spectra. And as you can see, the PCA method is the best method. You can see the residue. Here is a composite residue average of a lot of residue, and you can see the PCA component. If you're using five PCA component, it's already very good. And if you are using 10 templates, it's also it will be getting better. And it doesn't mean the other templates are not good enough, because here we have a problem here. It means we for the PCA method, there's no issue of the no resolution issue here, because the PCA templates is just come from the sound spectra. But for other templates, their resolution is not exactly the same as the sound spectra, and they just their average resolution is similar to the sound spectra. So sometimes they will have some residuals much stronger than the PCA method. So here, if you just want to separate this host component and agent component, I suggest use the PCA component. And if you want to get the exactly host component, I suggest you use the PPXF to fit the original data. And we have in our code we have incorporated the PPXF function. You can directly use the PPX function in our package. And here's
Can I ask a sort of follow-up question on that? So you said for the PCO3, you can also choose the number of components. What does that actually set? Do you then have 5 stellar populations, or what does that mean?
Here mean for the PCO3 templates, here I just totally they have 39 templates, and here I just select 1/3 of the templates, or you can use all the templates, and you can choose according to a grade, and like according to the metallicity, and also other like ages. So you can choose a template by yourself depending on what you want to get. And here you if you want to test different templates, we just choose different choose different parameters with separation like this, just like in a grade.
Okay, thanks.
And next, six-figure is a successful rate as a function of signal noise ratio and the fraction of the host component. And you can see if the spectra have a very high signal noise ratio, there's no problem to do the almost no problem to do the separation. And but if if the signal noise ratio is lower, then you maybe you will meet some problems. And also for the host fraction of the host component here, here we test here is 0.3 and 0.5 and 0.7. If you get a even lower host fraction, you will be more more difficult to separate these two components. And so it means here two things. One is signal to noise ratio, and another thing is a fraction of the host component. And but very unfortunately for the some spectra, most of the spectra with a very low signal noise ratio, like around half of them signal noise ratio is below 5. So if we want to do the host decomposition, it's very difficult for the whole sample.
There's another question.
Yeah.
Hi, Hengxiao. How do you define the success ratio?
Yes. Here I just use let me think about this. I'm a little forgot about this definition, since this is the student doing the work, and I guess we just use like here we just use this criteria. If we got this warning, we just think this is a failed decomposition.
I see.
If we got some negative host component, host flux. And the next is fit agent continue, and here agent continue here is not just only the power law. We also in our code we also consider the ion emission lines, also the polynomial component, and also the binomial continue as the agent continue. And here is the example of the spectral fitting for the continue, and you can see different components. And here I want to emphasize the polynomial component, and you can see there's a model degeneracy between the power law and also and the polynomial component. And for this object, you can see the power law is dominated, and for the at the level of the spectra, you can see the polynomial is already dominated, and at least have some equal fraction. And so if you want to do a local fitting for the spectra, like just you are only care about the H beta region, I suggest you to turn off the polynomial component, since the power law is already enough to do the fitting. And if you doing the global fitting, like fitting the fit for the whole spectra, and I suggest you to turn on the polynomial component, since it accounts for some reasoning for the spectra, and also in the agent composite, we know that we usually sometimes we need a broken power law to do the fitting for the continuous. So polynomial sometimes is another thing similar to the broken power law. And if your science is focused on the index of the power law, maybe you also need to turn off the polynomial component, since if you are turn on the polynomial component, it's meaningless to study the power law index, since the model degeneracy. And the next slide is the UV optical ion templates and its binomial continue, and you can see the UV templates consists of 3 different colors, and they come from different papers, and we choose these three iron templates because they are best at the time, and we are just using the Broson's optical templates. And here is a comparison between different templates, and you can see the main differences around the emission line region, and because it's difficult to separate the broad emission line and the iron templates around the emission line region. So so recently, Dyson Park have studied Mark 493 this object, because this the iron emission in this object is the line width. I should say the line width is narrow in this object, and also it suffers less extinction for this object. So they build a new iron template around the H beta region, and they claim that this template is better than other templates. So maybe in the future we will add these new templates into our optical iron templates. And here also we have a Balmer continuum, and we just use a power law to mimic the Balmer continuum. And I suggest you to turn it off if you don't care about the Balmer continuum, because only when you want to study the like a Balmer edge, you can turn on the Balmer continuum. And also the Balmer continuum have a model degeneracy with the power law. Both of them are a power law. So sometimes the Balmer continuum will be dominated, and sometimes mimic the power law. So sometimes we should turn it off. And also, this is not a perfect model, because we just calculate a model of the blue world of the Balmer continuum. We didn't consider high order series of the Balmer emission lines here. And also, if you turn this on, the code will be pretty slow. So so it's not sometimes for a large sample fitting, you don't necessarily to open it. And here actually this is a diffuse continuous emission, and Balmer continuum is just a small part of but a major part of the diffuse continuum. This diffuse continuum is from the borderline region, and you can see there's three features in this picture. One is the alpha scattered llama alpha line, and another is the Balmer continuum, and you see the Balmer jump, and also the Paschen jump here. And if you want to do the fitting for the Balmer edge, maybe you need to add another component, is high order Balmer series emission lines here. And like fitting here, you can see we are using a diffuse continuous emission template here to mimic the whole to represent the whole emission from the diffuse continuum, and including the Balmer continuum. And you can see we still have some problem here, because this here we caused by some very high density clouds in the borderline region. There's a real shift for the Balmer continuum. So we are still not very clear about the physics around here. So we haven't decide a perfect model for this region. So but our code is ready, and if you want to use this code to do some science for the Balmer jump or Paschen jump, you can I can provide this code. And also, as I mentioned before, for the quasar component, usually we need to have broken power to do the fitting, like around here 5,000 angstrom. There's a turnover here, and here I just show example of broken parallel fitting with our code. And here I use 4 broken parallel to do the fitting for the self-massive binary science. So this just tell you we can do that, but in PyQSOFit we just use a polynomial component to instead of the broken parallel. And the next part is fitting the emission lines, and we just use a narrow component and broad component. And here I just show you some examples here. And at first glance, maybe you will feel this is a nice fitting, but actually you can see the narrow component here is not fitted, and obviously the narrow component is too broad here, and you can see this software 2 is also not well fitted. And what you need to do is change the parameters, and here the problem is because for in our input parameters we have three different kind of component. One is broad, and it's around 0.004 to it's above 2,800 kilometers per second, and the narrow component is below 1,200 kilometers per second. And we also have an intermediate component between this narrow component and the broad component. And obvious here, the broad component is just is around the filling the narrow intermediate component. So here the problem is this parameter is too large. You need to get a small lower limit for this component. So if you change it to 0.001, you can get a nice fitting like this. You can see the narrow component can get a very perfect fitting for this region. And here there's another problem, and because you can see for the narrow component in H beta it's around 370 kilometers per second, but for oxygen 3 the line width is much larger. And if you want to make them consistent with each other, and also get a better fitting for the oxygen 3, you can see you can also do fine tune the parameters, like you can combine these two complex and merge them together, and so that you can tie the line width between different complex. So if you believe your narrow H alpha is have the right width, so you can just tie the oxygen 3 to this width, then you will get a nice fitting. Like here, there's a core component for the oxygen 3, and also have a wing for this component. So the line width for the oxygen 3 and narrow H alpha are the same. And also here we have some abnormal spectras for the here, like disk emitter and some double peak spectra here. And here I just want to show you a fitting for this object. And what you need to do is make sure the since the broad component here is very broad, and there's a strong shift for the broad component is around 8,000 kilometers per second. So you need to make sure the broad component is the complex is large enough, and also you need to make sure the velocity of the broad component is large enough. Here 0.05 means 13,000 kilometers. It's already large enough. And also you need to add another emission line like 0.01 here, and then you will get a fitting like this. Next is for an absorption line quasar, and you can see there's 3 systems one is the emission line, and two systems of the narrow absorption lines here. And here I just want to show you the ability of this code. We can do the fitting for the narrow absorption line, but it's manually, not automatically. So you need, if you want to fit the narrow absorption line and some narrow border emission lines, you need to manually control the parameters. And finally is run the error analysis, and we have two kind of methods. One is the Monte Carlo method and just randomize the flags according to the uncertainties and refit the spectra over 15 times. It's very slow. And if you are using the MCMC method, and usually we set the n sampling to 200, and for each fitting, like for the continuous fitting and each line complex, you will get a corner plot like this, and every parameters are plotted here, and you can get the error distributions of every parameters. But the main problem here is in the spectral fittings, the error is dominated by the systematic error and not the statistical error. So we are currently exploring a fast and reliable new method to estimate the systematic error, and we are trying to use different models for the continuum and emission lines to estimate the systematic error. And like for example, for continuum, we can turn on the polynomial component and turn it off to compare the difference between two kind of methods. Then you can just fit the spectra twice to get the error. And or for the emission lines, maybe you can use Gaussian like two Gaussian components and three Gaussian components to compare the difference to get the error. And another idea is maybe we can use the smooth spectra to estimate the systematic error. We are still exploring this. I'm still not sure about the system method. And finally, is some future prospects, and in the future for the PyQSOFit, we will add some specific updates, like write a doc for this code and improve the host decomposition method, and also the error estimation method, and also like speed up the code. And but in the big picture, we want to update our single epoch spectra to multi-epoch spectra fitting, like for the IM science. And also we want to update this code to fit for to meet the IFU fitting requirements. And here I just show you some example for the multi-epoch spectral fitting. And this is an object come from stone IM, and the gray spectras are a single epoch spectra, and the red one is a mean spectra. For when you get a lot of spectra for the same object, and you need to do the normalization for different epochs. Like here, I just normalize to oxygen 3, and then you will have a mean spectra, and you do the spectral fitting for the mean spectra, and you can fix the narrow component in this spectra, and then apply this narrow component, fix this narrow component, and fit the single epoch spectra for the broader component. Then you will get a borderline only RMS spectra, like here for the H beta. Then you will able to calculate the line sigma, so you can so that you can get the black hole mass of this object. And here we also do the spectral decomposition. If you want to get some host property, you can input this. You can transfer this host galaxy to the PPXF and do the fitting with the PPXF to get some parameters. And also, here's an example of the IFU fitting, and here's a agent in Manga, and we are just using our code to do the IFU fitting. Here you can see in the center, here's one spectrum from the center, and you can see there's a border component, and we are using our spectra. We can using our spectrum code to do the fitting for each pixel. And if you want to get some host properties, we just use PyQSOFit. And here the main results, we can get the velocity map and the velocity dispersion map, and also the broader component flux density. So summary, for the summary, I just want to I suggest you to when you're using this code, I hope you can understand what you are doing and know how to figure out the correct setups for the line parameters and the keywords, and also try to understand the outputs before you are using for science. And if you are if you can understand, you can read the source code, maybe you can change the source code by yourself and certifies your own requirements. And the limitation of this code is just as a low, we can't fit a lot of low signal noise spectra and some ball quasars, and also the code is a little bit slow. So I will stop here, and if you have any people want to update this code, we are always welcome, and thanks for your attention and using our code. And next, I think Qiaoya will talk about his application to the stone spectrum.
All right. Well, thank you very, very much for this overview, and let's take a quick break and see if someone has a question.
Let me show myself. Okay.
Can't believe that no one has a question. Well, then I ask one. So I was not so clear on how was the PCA constructed so that it knows what to do, where the lines are. How is the PCA line free?
You mean how the PCA components are constructed? Or,
yeah.
Yes, this is you can take a look at the Yip's paper in 2004, and they have they just using the a large sample of quasar and using the PCA method to separate the different component in this sample, and they will get some main templates like order 1 template and order 2 template, and for instance, you can just choose several first order templates to get a nice fitting for the quasar spectra, and they are using the same method to get the PCA component, different component for the host. Yeah, if you want to know the details, you can read their paper. Yeah.
Okay. Katharina.
Thank you for the presentation. I was just wondering if there is a way of systematically fit several spectra at a time, or if you just suggest doing one at a time and then checking its specific configurations.
You mean we can with a certain if you want to fit a lot of spectra, I think with a certain input setting for the line parameters, you can get the perfect fitting for all the spectra.
Okay, I'm sure there will be more questions and we have time later. So, but in the meantime, let's move on to Qiaoya's talk. Please go ahead.
Okay, so I'm going to give a brief talk about my, nope, sorry. Okay, so I'm going to give a very brief talk about my project on using the PyQSOFit into the Sloan Data Release 7 Quasar catalog. And I really hope that Hengxiao could give this talk earlier, so I don't have to feel so struggle. So in the data release 16Q, we have around 700,000 quasars from the data release quasar catalog presented by Lin et al. 2021. And in this talk, I mean, most of the Hengxiao's talk have give very detailed description, but I made some my own modification to the PyQSOFit. Here I'm using the version 1.1, which version 1.2 I believe is released very recently. So there are some minor difference, but you can always change the code to your own. And here I list some of the line fitting parameters here, but it's not very detailed. Like I tied some lines and parameters that if you are interested, you can just send me an email. I will send the file to you. And here is the function setting to my function setting of the PyQSOFit in my code. And here the 3 red square, I point out some of the difference between my version and the original version 1.1. And I'll give a very brief talk about this. So first I tied more lines because the version 1.1 can only tie 2 groups of lines, as Hengxiao have said earlier. And then I made some modification to the local fit. So the PyQSOFit use a global fitting, and it's not like fit the whole spectrum. It fits some specific continuum window, and which do not cover some of the lateral lines. So I give 3 examples here for Kcm2, oxygen 2, and nitrogen 5. The blue line here shows the global fit result, which is not as good as the local fit for these 3 narrow lines. So I recommend for some narrow lines, you could consider using local fit instead of the global fitting result from the PyQSOFit. And also I realized during the fitting, there are some quasars that have some absorption lines in the line in the emission lines, which could destroy the fitting. Sometimes it looks very bad. So you have to remove those absorption pixel from the fitting, so you can so the fitting will looks much better. So I made some modification to this part. And the other difference is because we feed the host, we use the code on a lot of quasars. So if anyone wants to check the results later, they could use I gave a tutorial on the GitHub. So if you want to check that, you can use the tutorial. And the original PyQSOFit output, the fits file only saves the major results, which is not enough if you want to take a more detailed look at the specific quasar that you are interested in. So I changed the output file format so you can check the what the result looks like for each quasar. Like you can check the major result, add more properties in there. And the second extension, I saved the MC results because the MC result is not saved in the PyQSOFit. And third, I saved the spectrum for people to check the result by their using their own eyes. So I think that's all I have. Very brief about PyQSOFit. If anyone has any question, you can just talk to me or send me an email.
Thanks a lot. Are there any questions? I will start with one. So you chose some settings, and did you do some tests and then decided, oh, it doesn't work, and I will change my settings, and then it worked better? And if you did, based on what did you judge that?
You mean the local fit, or which part are you referring to?
Well, so you were saying here, for example, that you tied more lines.
Yes.
So I guess you found out that the default, or what it was doing before, was not suitable. And
Yes.
then you made some changes, and then I guess you were happy with the result. And what
Yes.
did you look at to judge that?
I mostly look at the residual chi-square to judge that. I mean, if you set different component, you tie different number of components, the result will look slightly different. So I use the chi-square.
Mm-hmm.
Yeah. And since I applied the same fitting parameters to all the quasars for the 700,000 quasars. So there might some quasars might look better if I tie less lines, but I only did very limited experiment on quasars. So I think my current parameter is working for most of the quasars, and that should be enough, I think.
Mm-hmm. Yes, I mean 700,000, that's quite a sample to work with, and you probably don't want to look at every single one of them.
Yeah, I checked like a few thousand and it looks good.
Mm-hmm. And how long did the fitting actually take on such a large sample?
Roughly a month, I think.
Mm-hmm. Ah, finally.
Yeah, you can change it. Yeah. I think Katarina has some questions.
Yes, thank you for the talk. I still kind of have the same question I had before. So in your case, did you have to somehow separate the objects by redshift to make different parameters in order to make all the fits at once? I mean, how did you use the parameters to such a large sample?
These are my parameters. So I think, sorry, I don't think I understand your question correctly. You mean you have a large sample and you have different redshifts, and what is your question? Sorry.
My question is, for example, you used only this piece of code, these parameters and this specification for
Yes.
all the thousands of objects that you have?
Yes.
Oh, cool.
Yeah, I did many modifications to the fitting parameters. And if you're interested, I could definitely send you the more detailed fitting parameters.
Thanks. I will have a look at your GitHub and probably get in touch. Thank you very much.
Oh, I didn't put those two in the GitHub, so if you want, sorry, I could send it to you. Yeah.
Yeah, I think this related to some issue we encountered. So if some line complex moves out of your observing window, you can still
Yes.
fit. That's what you're saying. You fit, but then you might ignore the results. Is that what you're doing?
You mean the line is moving out of the window?
Yeah, at some redshift,
I mean,
right? Not
so
all your lines will be
yeah,
seen.
at some, I think you can just modify change the fitting window for those in the fitting. But here sometimes the redshift is not correct. So you won't find any lines within the window, because if the redshift is correct, you should, because the window is quite large compared to the lines. So normally you should find that. If you couldn't find that if you couldn't find the lines for most of the windows, for most of the complex windows, I think that you should check the redshift.
All right. So, okay, sorry, I wasn't very clear. What I meant is, for example, H alpha at some redshift
Yes.
will not be observable by SDSS.
Yes.
But you can still run with that complex included in the configuration.
So the code can check if the spectrum range does not cover the complex parameter, it won't fit for the complex.
I see. Okay. Then let's move on to Blessing, I think was next.
Thank you for the talk. May I ask how you fit your O3 line, for example, the parameters you applied, if you apply like the flux ratio or something like that?
Sorry, oxygen 3, you mean?
Yes.
Oh, wait. Oxygen 3. Okay. I didn't show the example here, but I think most of them are very similar to the other lines. I don't think we need to make much changes in the oxygen 3. It's very similar to other lines. It's within the time window of it's within the time window of H beta line. So it's like H beta have many components, and you can see the subcomponents in each in the line parameter, and it will fit for those.
Oh, okay.
Sorry. I'm not sure if that answered your question. I feel like because oxygen 3 doesn't have much difference with other from other lines, so it just change your parameter and add that component into the code. That should be enough.
Yeah, I was wondering
for the oxygen 3, sometimes you need to add as a wing component, so made it a little complicated compared to the other emission lines, as a narrow emission lines. So you should be very careful for the wing component. Sometimes it will be you will mimic the very broad component in H beta. So
yes,
you need to be very careful.
Is that answer your question?
Yeah, probably. You said I would go and look on the GitHub, but you said there is no, that file is not there. Because I would want to look at. First of all, I was wondering if you put like a flux ratio.
Yes, you can definitely put a flux ratio, but I didn't do that here. So
Okay.
but you can always change the parameter because PyQSOFit looks different.
Yeah, because I wanted to use these the values from this catalog for the O3 line. That's what I was asking.
Sorry.
I was asking because I wanted to use the values from this your work for the O3 line. That's why I wanted to know how you actually fit the O3.
Oh, I can send you the parameters I fit for the core component and the wing component. And you should, yes, and you should be careful, as Hengxiao, you should be careful about the weights of the wing component, because sometimes, yes, it would mess up. But if you set the parameter, like you can adjust the parameter very carefully, and you can get what you want, I think.
Okay, perfect.
I think Chen Yang has some question.
Oh, hi, Qiaoya.
Hi.
Nice talk, thanks. So I'm just wondering, do you have an estimation of the fraction of, like, for your global fitting, the fraction of objects with a larch chi-square?
I didn't have that, but I think most of them looks good for the chi-square. Only for the continuum, you mean?
Yes.
I think most of them looks good. I think the ratio would be more than 90%.
I see.
Maybe 95%, because most of them looks pretty good.
Mm-hmm.
Any more questions?
Blessing, do you have another question, or is that still the hand from before?
No, I should put down my hand, sorry.
Okay. I had another question in the meantime. How does PyQSOFit guess where it should start to fit, the initial parameters where it starts to do the least squares?
So you do some process to the spectrum first, and then I think you cut each complex. Like for H-alpha, you cut the wavelengths between 6400 and 6800, and then the initial component is based on the input parameter Hengxiao gave in the very beginning. He gave a table that he would look for emission lines around the central region, and it would just change the parameter shifting around that region. He gives a table somewhere. So the initial Gaussian is based on the input parameter you gave the code.
Right. So I guess the wavelengths are all centered at what they're supposed to be, and then I wasn't sure whether all
And
the
then
parameters of the Gaussian are set, like the location, width, height, and also the PCO3 and the PCA, right? They also need to be guessed initially, I guess.
I didn't use the Galaxy host decomposition in my code, so I think I'll leave that to Hengxiao. I didn't dig into that very much.
I won't say the initial value is not very important. Not important. So you just need to give an initial value between the lower boundary and upper boundary. And what you mentioned in the host, you just mentioned the initial keywords in the for the host decomposition or something.
Sorry, I didn't quite understand.
I mean, you just mentioned the host decomposition keywords or something else.
Well, I was wondering, the first step is the continuum fitting, right? With the host decomposition.
Yeah. No. So yeah. The first step is the host decomposition, and then we will do the continuum fitting and then the emission line fitting. They are separated.
Yeah, but also here in this step, it needs to guess some initial values, and then it does the least square, right?
Yes, the initial value, I already have some default settings. I just mentioned the initial value is not very important, and you can always get your final fitting result very nicely, not strongly depending on the initial values. So you don't need to change the initial value.
Okay, but it could be provided in the command line or in the
Okay. Only one I remember in my according to my experience, only when your narrow line is too narrow, sometimes you maybe need to set a lower initial value so that the fitting will work nicely for the very narrow emission line fitting. Yeah.
Okay. Sophia?
Hello, very nice talks, both of you. Very interesting to hear more about. I had some questions about the fitting of the broad H beta component. So what is the minimum width that the broad line component can have? Or is this, like, I guess this is something you can set?
Broad component?
You mean you can answer.
If you want, I'm setting the broad component lower limit to, I think I'm setting 0.02, which is around 2000 kilometer per second. Whatever.
Okay, my question was about the identification of narrowline C4 galaxies, which have broad line widths of less than 2000 kilometers per second. So I guess your method would kind of miss those, because you wouldn't be able to find one with a width of like 800 kilometers per second.
You can also say the narrow component, which with a different range.
I know, but they have a narrow component and then they have a narrow broad line. So the broad line width is relatively narrow.
Yeah, the situation is like this. If you set a lower limit around 2000 kilometers per second, you will miss some very narrow component, and
Yes.
So I think in Charles samples, all the quasars are with very broad emission lines, and maybe only a very few objects will have this situation. So maybe if Qiaoya can check their sample, maybe they can find some.
Yeah. I can check my sample. Yeah.
And
I think it's about
usually
10%.
Maybe.
What?
Oh, 10%.
I think it's about 10% of broadline, of broadline AGN are narrow line safer ones, but that could be wrong. I think it depends on different, factors.
Yeah, I think if according to Qiaoya's setting, if there are a lot of narrow line SDSS-V galaxies, I think if their narrow up limit is lower than this value, and maybe I think according to the logic of this code, maybe they will the narrow component will be the dominant component for the narrow line SDSS-V galaxies. So maybe they can also get a nice fitting for this kind of object. But I maybe they still need to check their fittings. Maybe, yeah.
Okay.
Yes.
And would there be some value for the width of the broad line, at which point you would no longer trust it? Like, do you think you could realistically fit values of 1,000 kilometers per second, or do you think that the error would be too large and you'd just get degeneracy between the broad and narrow components?
Sometimes this could
Maybe
happen.
You don't know.
I actually don't know. I didn't say those examples. I didn't say those, but
Okay.
I think sometimes this could happen. Yeah.
Okay, thank you.
Okay, are there any more questions? Doesn't seem to be the case. So I saw the code is on GitHub, and I guess I don't know, how long has it been on GitHub now?
You mean the PyQSOFit new version of PyQSOFit?
PyQSOFit in general.
I
So
think
old version is already 4 years for the old version, and in the new version is we are still working on the new version. So we are keep updating this new version, and I suggest if you want to use this code, maybe it's better to use the old version. But if you want to tie a lot of lines, maybe you can use the new version. But maybe have some risk for using the new version, since we are still haven't tested this new version. We are still updating the new functions for the new version. So after we doing some tests for the new version, maybe it's safe to use it.
Mm-hmm. Okay, great. And I guess people can either email you, you were on the email, or open issues here and communicate on this page.
Yeah. If they have any problems, they can leave a message on this page or just send me an email.
Okay, great. Well, thanks a lot. It was a whole array of wisdom and useful tips. Much appreciated. And I will say thank you again. And I'm sure everyone agrees here. And we'll close now the recording.
Hosting.